So good evening everybody, and thank you for this opportunity to talk to the Astronomical Society of Botswana. So this is about the legacy of the Hubble Space Telescope, and there can be very few scientific instruments, let's face it, that's what it is, there can be few scientific instruments that are as iconic as the Hubble Space Telescope. I think not only would every astronomer recognise it instantly, but I would argue many people around the world who don't have a passion for astronomy would still recognise this. So what I'm going to be talking about this evening is to introduce the idea of a need for a space-based telescope and talk briefly about ground-based alternatives, and then look at the history of how the Hubble Space Telescope came to be, how it was launched with an imperfect mirror, and how the optical problems were fixed. And then looking at what the Hubble Space Telescope has done for our understanding of the way the universe works and the way the public has come along for the ride. And then I'll finish by coming back to the need in the future for space telescopes and again ground-based alternatives. So this is a useful comparison of the sizes of various telescopes either existing or planned for the future. In the top centre, in yellow, you can see the world's largest telescope at present, the 10-metre diameter. It's difficult to define a diameter when you're talking about hexagonal segments, but approximately 10 metres in diameter, the Gran Telescopio Canarias. And all of these telescopes are to scale in terms of the area of their collecting mirror, and you can see that on the right hand side there are some truly monster-sized telescopes that will be coming along shortly. The 30-metre telescope and the European Extremely Large Telescope are indicated there as planned for 2022. Perhaps don't take that too seriously, there are a few delays on both of those telescopes. But for comparison, down in the bottom left, there are the space telescopes. I'll be talking about the Hubble, of course, I'll be mentioning the James Webb Space Telescope, and in passing I'll also mention the Kepler and Gaia telescopes. But you can see instantly that they are much smaller than their ground-based counterparts. This is no surprise. To get a telescope into either Earth orbit or orbit around the Sun, that's a lot more difficult than building a ground-based telescope, so no surprise, space-based telescopes generally are smaller than their larger earthbound counterparts. But when we think about telescopes, we have to remember that of course they have come an awful long way in 400 years since Galileo. We know that of course telescopes using lenses have given way to telescopes using mirrors. The largest refracting telescope was the Yerkes on the left hand side there, with a lens about a metre or so in diameter. Anything larger than that is impractical. And the quest for ever larger and larger apertures, whether it be lenses or now mirrors, that's been driven by two principal factors. Larger mirrors will collect more light, so you can see fainter objects, and larger mirrors for a given wavelength of light will be able to see more detail. They'll have higher resolution, and so either you can see smaller objects or more detail in a given sized object, or you can see similarly sized objects at a greater distance. So there's two good reasons why you always want to have telescopes with larger and larger mirrors. But if we've got lots of large telescopes on the ground, why put a relatively small telescope in Earth orbit? And the reason of course is to get above the Earth's atmosphere, to get above the blurring effect of the Earth's atmosphere so that we can get truly diffraction limited images that are only limited by the size of the optics, not limited by the blurring effects of the Earth's atmosphere. To put that into context, it's been estimated that if we have a telescope on Earth the same size as the Hubble Space Telescope, it would have a resolution some 10 times worse because of the blurring effect of the Earth's atmosphere. So although the telescope mirror in the Hubble is a mere 2.4 meters in diameter, it packs a punch above that size simply because it can work at the limit of the optical capability. So let's have a think about the history of how the Hubble Space Telescope came to be. When did it start? Well, perhaps earlier than you think. As way back as the 1970s, men were still stomping around on the moon when NASA were thinking about building a large space telescope, what was called at the time simply the LST. That was the first milestone, getting some designs on a drawing board. The second big milestone, it was cancelled. 1974, Congress said, great idea guys, but way too expensive. So, of course, there was an outcry from the scientists who said we really need a telescope like this, and so it was agreed that there would be some funding for a space telescope, but NASA could only afford that through Congress funding if they paired up with the European Space Agency and ESA took some of the financial hit. So in 1978 it was agreed that Congress put money towards the Large Space Telescope. So although quite often it's thought of as a NASA instrument, it is a NASA-ESA instrument. So the tasks were put out to tender. The spacecraft was put out to tender and was put out to Lockheed, and the telescope itself was Perkin-Elmer. Bear in mind that NASA don't treat the Hubble Space Telescope as a telescope as such. It is a spacecraft, and it's a spacecraft that has a telescope inside it. That's the way NASA deals with their technology. So in terms of the expertise in building spacecraft, that went to the Lockheed company, an aerospace company who know how to build aircraft and spacecraft. And the optics inside the spacecraft, that was tendered to the optical company Perkin-Elmer. So in 1979, construction of the primary mirror began, and Perkin-Elmer produced the 2.4 meter diameter mirror. And in 1981, they had finished figuring it and polished it and declared it as finished and declared it as essentially perfect. In other words, everything ran okay in terms of the grinding of the mirror, the figuring of the mirror, the polishing of the mirror, and therefore at that point the idea of having a backup mirror was put on hold. The idea of a backup mirror was an essential contingency plan just in case Perkin-Elmer had any problems making the main mirror. It was realised that the primary mirror was absolutely crucial to the whole project, and so it was insisted that there was a backup made completely independently, manufactured and tested completely independently of Perkin-Elmer's, and that was done by Kodak. But when Perkin-Elmer declared in 1981 that their mirror was finished and was fantastic, at that point the backup mirror made by Kodak was simply put into mothballs. It was simply abandoned and put into a museum. 1983 was the original planned launch date, and at that point the LST was named the Hubble Space Telescope in honour, of course, of Edwin Hubble, who had done so much pioneering work on looking at the recession of galaxies because of our expanding universe. But there were further delays even from 1984. It was put back a year and then another year and then another year because of scheduling slips both from Perkin-Elmer in the optics and from Lockheed in the manufacture of the spacecraft itself. By 1986 the budget had hit something of order $1 billion and was getting very expensive. It was still rising at that point. And although it was hoped to go into orbit at around that time, unfortunately the Shuttle Challenger disaster occurred in 1986 and that grounded the American shuttle fleet. And therefore it wasn't until some years later that the Hubble Space Telescope finally was launched into Earth orbit in 1990. As you can see, by this time it was already quite a few years late. And by the time it went into orbit, the construction costs were estimated as somewhere around $2.5 billion. And that's not taking into account the various costs of the shuttle maintenance missions that occurred in later years. So a very expensive project. One thing that's worth mentioning for what comes later is the design of the mirror. I'm not going to get too technical on the optics here, but the Hubble Space Telescope has a particular design of optics called a Ritchie-Chrétien design. And in that design, the primary mirror is a shape called a hyperbola. So we talk about hyperbolic optics. Now, up to the middle of last century, all big telescopes had parabolic mirrors. And the last major telescope to use a parabolic mirror was the Hale telescope at Mount Palomar, which has got a 5 meter or 200-inch mirror. Now, why does that matter? Well, it matters for what comes later, because a parabolic mirror is the shape that you need to take light from infinity and bring it to essentially a perfect focus. A hyperbolic mirror doesn't do that. A hyperbolic mirror has to work in conjunction with another mirror. In other words, there's a primary mirror and a secondary mirror, and both are required to bring the light into focus. And that means trying to work out whether you've got the right shape, the right hyperbolic shape, is rather tricky, and that's relevant for what we'll see in just a moment. But only when, in 1990, when the Hubble was put into orbit, did the horror slowly dawn on those responsible for commissioning the telescope. They could not get it to focus correctly. What they were hoping for on the left was nice, sharp, stellar images when they pointed at a star field. But what they were actually getting was relatively compact stars, but surrounded by a horrible halo of light. And they were trying to work out why that halo wouldn't go away as they continuously tried to focus the telescope, made sure that they had allowed it to cool down correctly. No matter what they did, they could not get it to focus correctly. And after a while, they had to admit that the primary mirror was suffering from an error called spherical aberration. Let's just make sure we understand what spherical aberration is. Let's imagine we have a mirror that should focus. So let's just assume it's parabolic. It doesn't really matter the fact that it isn't for the moment. Let's assume that we have a parabolic mirror focusing light from an infinite distance away. Light that hits near the center of the mirror comes to a focus. And light that hits different parts of the mirror should come to the same focus. But spherical aberration means that the mirror has been made incorrectly to the wrong shape, such that light hitting further away from the center of the mirror comes to a focus too early, as indicated by the red lines there. So when we try and put a detector at the focus of the mirror, we can't find anywhere to put the detector where all of the light is being focused correctly. If we put the detector where most of the light is focused, then you can see that light from the edges of the mirror is coming to a focus too early before the detector, and then produces a halo around the stellar image. And that's precisely what occurred here. So spherical aberration is called spherical aberration because it's an aberration that occurs for spherical mirrors. We're not saying that the mirror was ground into the shape of a sphere, but that particular type of aberration, when light hitting the edge of the mirror comes to a focus too early, is just generally called spherical aberration. And that, it was realized, was what the problem was here. So remember that what they wanted to see was what was going on in the lowest panel here. They wanted to see nice, sharp star images, but they were getting horrible halos around the images. Just for comparison, you can ask, well, what would the telescope have produced in terms of star images if the telescope was on the ground? If you took a 2.4 meter diameter telescope and stuck it on a mountain top somewhere and looked through the Earth's atmosphere, then you would get an image similar to the panel at the top there. So this is a simulation of the star field below, deliberately blurred to simulate what you would expect from the Earth's atmosphere. And of course the resolution is not as good. So the middle image, in other words what the Hubble was actually producing, was still a little bit better than what you could get with the same telescope sitting on the ground. But NASA and ESA had just spent billions of dollars putting it into orbit to get away from this aberration, this blurring of the Earth's atmosphere. and yet they still have aberration present. So this looks like it is a complete white elephant, in other words, a complete waste of money. Why spend billions of dollars to put a telescope into orbit where you can barely get the sort of images that you would expect? So how could a mistake be made? How can you possibly put billions of dollars of telescope into Earth orbit with optics that do not focus correctly? Well, tests carried out during the construction indicated that it was the most precisely figured mirror that had ever been made up to that point in the 1980s. The surface roughness, the bumps, the hills and the valleys in the surface of the mirror that they had produced, the hills and the valleys were only of order 10 nanometers from hills to valleys. It's difficult to judge just how smooth a shape that is. 10 nanometers in a mirror that's 2.4 meters in diameter. You can get an idea of just how small those little bumps are by saying, if you were to take the Hubble mirror and scale it up until it was the size of the Earth, then how big would those bumps be? And the answer is a few centimeters. 10 nanometers on the Hubble mirror is similar to 3 centimeters on a disk the size of the Earth. So yes, it is a very, very smooth, very precisely figured mirror. Unfortunately, it was very precisely figured to the wrong shape. Somewhere they made a mistake. It was wrong by of order 2 microns, 2/1000 of a millimeter. And if 2 microns doesn't sound like much, remember that's much more than the wavelength of light. If you want to make a good set of optics, ideally you make all the surfaces accurate to a very small fraction of the wavelength of light, 1/10th, 1/20th, 1/50th of the wavelength of light. But here we have errors that are some 4 times the wavelength of light, if you take wavelength of light as being about 1/2 of a micron. So very precisely figured, but the wrong shape. And it comes back to the fact that if we had started with a parabolic mirror, you can test that by taking light from infinity and check it comes to a focus. But with a hyperbolic mirror, it'll only focus correctly with a second mirror. And you can't really grind and figure 2 mirrors at the same time and test them at the same time. You really need to test them separately. So how do you test such a mirror? Well, you need some extra optics in order to test this peculiar shape of a hyperbolic mirror surface. And the particular test rig that was used by Perkin-Elmer requires a little bit of optics, usually lenses and mirrors, that are called a null corrector. We won't worry about the details, but this particular combination of optics is required in order to test the hyperbolic mirror. And the problem was the null corrector was misplaced in the test rig. In other words, the test rig itself was set up incorrectly. So they were trying to check that the mirror was correct using a test rig which was giving them the wrong data, and hence the mirror was ground to the wrong shape. As Homer Simpson would say, "Don't." A simpler test would have revealed the fault, but Perkin-Elmer deemed it as unnecessary. Why do a simple cheap test when they've done a very sophisticated, very complicated, very expensive test which has told them that everything was okay? What a shame. And of course there is a backup mirror made independently of the Perkin-Elmer test rig, so presumably that one was ground to the correct shape. Ground and tested. But it's in a museum. It is not in the telescope in orbit. So what are NASA going to do about this calamity? Having spent billions of dollars of taxpayers' money, both in America and in Europe, they now have something that doesn't work. Well, one thing basically saved the Hubble from a complete and utter disaster. And that is the idea that from the outset it was designed to be serviced by shuttle astronauts. On the ground there was a copy of the camera, one of the cameras that was in the Hubble. I will mention again in a moment that the Hubble is not simply a large camera. It is a set of optics which can feed the light to one of several instruments, at the very least different cameras or different spectrometers. But in particular, there was one camera that was duplicated on the ground. It's not that unusual when you have a space mission to have various instruments which you build and take on the flight, and duplicates which can stay on the ground for testing purposes. So NASA had a duplicate of the main camera, and they realized that if they could tell what the problem was, they might be able to deal with it. So by going to Perkin-Elmer and checking the test rig, they found the error with the test rig, which means they found out why the mirror was wrong, confirming that it had spherical aberration. Not only that, but they knew precisely how wrong it was. They knew that the test rig was incorrect, so they knew precisely what the figure of the mirror actually was, as well as what the figure should have been. So they knew what the optical correction necessary was. So just like anybody with poor eyesight might have glasses to correct their vision, they knew by how much the main mirror was off, and so they could figure out what would we have to do to the camera, what extra optics would we have to add in order to correct for the imperfections of the primary mirror. And they basically built them into the camera that was sitting on the ground, and basically then told the shuttle astronauts, go up and swap the camera that's in there with this new camera that has the optics corrected. That will work for the camera, but there are other things there. There are other instruments, not just cameras. So what's the solution? Well, the solution is to know the error on the main mirror and then insert some extra pieces of optics. In a sense, insert a Swiss Army knife of extra optics. A Swiss Army knife is something with lots of different blades that can switch out where needed. And in a sense, the same thing was done with the corrective optics, which they called CoStar. And the image on the left is CoStar, which is a little bit complicated, so there's a simplistic version of it in a museum on the right-hand side. And you can see there are various coloured arms, each of which has got a little mirror on the end. So what they could do is to take the light from the main part of the telescope, and before the light was sent to this camera or this spectrometer, one of these arms would open out to put a mirror into the light path, such that each of these little mirrors is made not flat but slightly curved to exactly correct for the error in the main mirror. And so depending on which instrument you want to send the light to, CoStar would introduce a mirror on the end of one of these arms that would unfold into the light path and send corrected light into the instruments. So, as I mentioned earlier, you must remember that the Hubble is not simply a rather sophisticated camera. At any given time, it's got at least 2 cameras and 2 spectrographs on board. And over the years, because of the ability to service them by shuttle missions, these have been swapped in and out quite a few times. One thing to bear in mind is that the telescope itself is somewhat smaller than the spacecraft, and the actual size of the camera that we saw before is quite large, but the size of the chip inside the camera is not particularly large. That's a little mock-up of it. The main CCD chip in the camera is only about 4 centimeters on a side. It's not that much bigger than the sort of camera that you might, a sort of chip that you might have in your digital camera. If you've got a digital SLR camera, the chip may not be much smaller than that. And when you think of the focal length of the Hubble Space Telescope, the cameras in principle could be wide angle or high resolution. That depends on how the optics are sent to the instruments. But the nominal focal length of the Hubble Space Telescope is about 58 meters. So you can realize that if the chip is only that big and the focal length is 58 meters, that's a reminder that the field of view of the Hubble is actually quite limited, quite small. Let me just blow that up a little bit so we can see it a little more clearly. we can see that within the spacecraft itself, the telescope in blue only occupies the central 50% or so of the spacecraft. The front of the spacecraft is really just a large sunshade, or lens hood if you like, to stop sunlight interfering with the imaging. There's the secondary mirror, which as it happens has to be a hyperbolic shape, and there's the primary mirror, which is also a hyperbolic shape. And you can see that behind the primary mirror, that's where we have quite a few instruments, either cameras or spectrometers. Now, I don't want to get too technical about how things were changed around, but I think this is interesting to give us a guide to just how complex the Hubble is. This is a timeline running from launch in 1990 up to relatively recently, 2020. And each of these horizontal bars is one aspect of the instrumentation in the telescope. So one of the first things that happened with the shuttle service mission number 1, was that the camera, I'm not going to bother explaining what all the acronyms are. All that we need to worry about here is that's a camera that effectively didn't work, and then that was replaced with camera number 2, which has got the corrective optics built into it. And remember, it was decided that a Swiss Army knife would be used to send corrected light to all of the other instruments. But to fit the Swiss Army knife COSTAR in there, they had to sacrifice one of the existing instruments. And it was decided that a photometer for measuring the intensity of light would have to be sacrificed in order that COSTAR was placed in its position. An asterisk here is simply my shorthand for, whilst they were there, the astronauts did a little bit of maintenance. Here on the gyros responsible for pointing the telescope accurately and keeping the stable pointing onto a particular star or galaxy during the exposure of the cameras or the spectrometers. And elec there simply means the electronics and electrical systems were given some maintenance as well. A few years later, Service Mission 2 replaced one of the spectrometers with another spectrometer, and similarly this spectrometer was replaced. Why replace the spectrometers so early in its life? Well, remember, this is now the late 1990s. The Hubble was designed in the 70s and built in the 80s, which means by the late 90s it's already getting old and technology moves on. So it was possible to replace those two spectrometers. Not only that, but the spectrometers on the ground had the corrective optics built into them so that they would work without needing COSTAR. If we move on a few years, Service Mission 3, you can see not much happened. They just basically replaced some of the failing gyros there to make sure that the pointing accuracy was maintained. Here I've labelled in grey a situation where an instrument is giving a few problems, either failing or not performing correctly. So this spectrometer was giving problems in the early 2000s. And Service Mission 3B, as well as tweaking some of the electronics and electrical systems, fixed that spectrometer. And the last thing they did was replace one of the cameras with another camera, the so-called advanced camera for surveys at the bottom here, again with its own corrective optics. So now, in the early 2000s, we're in the position where all of the instruments that were originally launched with the Hubble have now been replaced with the necessary optics to make sure they all perform perfectly, despite the fact that the primary mirror was made to the wrong shape. In the coming years, things started to go a little bit wrong. They had some electrical systems, they had a problem with the spectrometer, they had a problem with the camera. And the last service mission, carried out in 2009, essentially fixed all of those problems. Camera number 2 had been working well for over a decade, and that was replaced with the final version, camera number 3. Because COSTAR is no longer needed, remember each individual instrument now has its own corrective optics, so COSTAR is no longer necessary, so the Swiss Army knife was removed and put into a museum when it came back to Earth, and CoStar slot was replaced with yet another spectrometer. So at this point, the Hubble has got 2 cameras, but 3 spectrometers on board. Again, reinforcing the idea that in many aspects of scientific discovery, a spectrometer that can give you the spectrum of an object is often more important than a camera that can show you what the object looks like. Cameras show you what it looks like, spectrometers tell you what's going on and what it's made of. So in this case, the asterisks there tell you that everything was given an overhaul and a bit of maintenance, and for the next 10 years or more, everything seems to have been working very well. So although the last shuttle mission to service the Hubble was well over 10 years ago, everything has been working very nicely ever since. They did have a computer problem some months ago, but they managed to fix it using existing protocols. So, although that's a rather technical slide there, it gives you an idea of just how much is going on, and it's not just a telescope, it's a telescope with multiple pieces of instrumentation which over the years have been refined and extended and maintained to make sure that the Hubble could deliver over its 30 plus years of lifetime. So just how has the Hubble contributed to extending our understanding of how the universe works? Well, there are simply too many examples, and I'm just going to pick a few things out of the many examples of what Hubble has done for us in terms of extending our understanding. One of the first things it did was to look at stars in the Andromeda Galaxy. This may look like a little bit of the Milky Way seen in our skies, but this is the Andromeda Galaxy. Remember, the field of view of the Hubble is quite small, so it can't get all of the galaxy in. This is a little bit of the outer part of the Andromeda Galaxy. But because of the wonderful resolution of Hubble, it's able to pick out individual stars, and some of those stars are called Cepheids. These are important because they have a luminosity change. Their brightness varies with a time period that depends on their actual luminosity, their absolute luminosity. In other words, by watching how their brightness seems to change and making a note of what the period is, you can then relate that to the actual luminosity of the star. Not how bright it appears, but how luminous it actually is. And if you can see how bright it appears to be, and you know how bright it actually is, then you can get a measure of the distance to that star. So measuring Cepheids in the Andromeda Galaxy allowed the Hubble Space Telescope to gauge the distance from the Milky Way to the Andromeda Galaxy. Turned out to be 2.5 million light years. But that gave us a number that was more accurate than any previous estimate. And so at that one stroke alone, the Hubble Space Telescope effectively defined the size of the universe that we understand. Because the distance to more remote galaxies is based on our understanding of the distance to more local galaxies. It's the first rung of the distance ladder that allows you to then go beyond that to more distant objects. Hubble was one of the first telescopes to image exoplanets, planets around other stars. This might look a little odd, but remember that planets are very faint compared to the much brighter stars that they orbit. So in order to be able to image planets, you have to effectively block out the glaring light from the central star. Having done so, there's a lot of scattered light, which is this sort of red ellipse that you can see there. But in the inset we can see tiny dots which indicate there is quite definitely a planetary system around this star. But being able to image directly is only of limited use. Where the Hubble came into its own was the fact that it could actually take spectra of various exoplanets, not necessarily the one we were just looking at in the image there, but various other exoplanets had their spectra taken by Hubble to see if, for instance, there was any sign of water in the atmosphere of these exoplanets. This is a mission that will be taken up by the James Webb Space Telescope in the future, the idea of looking at atmospheres of exoplanets. By looking at galaxies that are relatively close to us, the resolution of Hubble allows us to see exquisite detail within the structures of galaxies. Not simply the spiral arms, but all of the structures in there, the globular clusters, the galaxy clusters, the star-forming regions, the dusty regions, and regions closer to the centre of the galaxy. And by looking at lots of galaxies with this sort of detail, that helps in our understanding of how galaxies formed and how they evolve. When looking at clusters of galaxies, Hubble has been pivotal in our understanding of how the universe works. It's produced a number of images along the lines of this one. This one is most noticeable because of what it happens to have caught in the image. Most of the most of the objects that look a little bit orangey here are members of a galaxy cluster which is in the foreground compared to the more distant galaxies which look a little bit bluer in this particular image. So we can get an idea of what's actually happening and why it's a rather busy looking slide here, but let's see what's actually going on. What we have is some foreground galaxies that are bending the light that are coming from more distant galaxies. So imagine we have one or possibly more galaxies in the distance here. The light doesn't simply travel in a straight line to us, or the Hubble Space Telescope. Because of the existence of all of these galaxies somewhere between the distant galaxy and us, they are bending the light in a way that was predicted by Einstein in his general theory of relativity. Large masses distort space, and light follows these distortion of spaces, and so a large collection of mass behaves a bit like a lens. So this is called gravitational lensing. And different paths of light reach the telescope from a distant source. And that means a galaxy, for instance the galaxy that's seen in this square next to this very bright star, which is of course much closer to us, this galaxy here is actually imaged more than once. That galaxy also appears here next door. It's the same galaxy, a little bit distorted, and it's actually the same galaxy up here in the upper left. The same galaxy imaged multiple times because light has taken multiple paths on the way from the distant galaxy to us because of the distorting effect of the mass in this galaxy cluster. But not only that, we can see that if we blow up this galaxy here, we seem to have caught 4 very bright dots within this distant galaxy. Is that 4 supernovae going off in the galaxy? Well, that seems very unlikely. In general, you would expect a supernova to go off perhaps once every century or so in any given galaxy. So the chances of 4 going off at the same time, very remote. So what's going on here is the very distant bluish spiral galaxy just happens to line up very closely with a foreground object. This orangey blur that we can see in the middle here is an object that's much closer to us but happens to line up in the same direction. And that object, again, is bending the light so that light from a distant supernova actually takes 4 different paths to reach us, and hence that supernova is imaged 4 different times. So images like this obtained from Hubble of various galaxy clusters have allowed us not only to get more information about how these supernovae have gone off and the information from that supernova imaged multiple times, but more generally, when it's calculated how much mass must exist in this galaxy cluster in order to bend the light in the way we see here, either to image a galaxy multiple times or to image a supernova multiple times, when we work out how much mass is required, it's far larger than the amount of mass that we can account for just by effectively looking at all the stars and looking at all the gas that appears to be in the galaxy cluster. There must be more mass that is not luminous, that is not found by looking at gas that is glowing or stars that are shining. This is what we call dark matter. And Hubble has accrued a huge amount of information by looking at images such as these in order to allow us to gauge how much dark matter exists in the universe. We still don't understand what dark matter is, but we now have a better idea of how much is out there. and we need to find other ways of investigating where all the dark matter is, and indeed what the dark matter is. The Hubble Deep Field, I'm sure, is the sort of iconic image that has been shown many times. It was a very important image taken in the 1990s, not that many years after the Hubble was launched. The idea is you point at a patch of sky where you don't think there's anything interesting going on there, and you expose for as long as possible. In this case, this means about 1 million seconds. In other words, about 10 days of exposure. Lots of shorter exposures added together. So there might be 2 or 3 stars in this image, but most of the objects you can see are galaxies. Some relatively close to us, but most of these galaxies are very distant, many, many billions of light years away. And remember that if an object is many billions of light years away, light will have taken a long time to reach us. And because the universe is expanding, that means the light from these very distant objects tends to get stretched out. So we know we're looking back in time when we're looking at some of these galaxies. And we think that these galaxies that were made a long time ago, in the very early stages of the universe, not long after the Big Bang itself, we believe that those galaxies will have been made of very hot stars that will be emitting a lot of their light in the ultraviolet and the visible parts of the spectrum. But because of the expansion of the universe, that light will have been stretched or redshifted to longer wavelengths. And so although the light might have been emitted as ultraviolet and visible light, it is quite possible that a lot of the light that we receive will end up in the infrared part of the spectrum. And I'll say more about that in just a moment. Let's remind ourselves that the field of view of the Hubble is very small. Remember, we're talking about a chip which is only a few centimeters in size on the end of effectively the world's longest telephoto lens, if you like, a 58-meter focal length. And so the field of view is tiny. There it is shown relative to the size of the full moon as seen from the Earth. Just to make sure the picture of the Hubble Deep Field wasn't a fluke, as well as taking the deep field from a patch of sky in the northern hemisphere, a little bit later they turned it to a patch of sky in the southern hemisphere and took another deep field and got a similar picture. Not identical, of course, but a similar distribution of galaxies that are close to us and galaxies that are very distant. There are thousands of galaxies in this very small field of view that the Hubble has, and simply by scaling up the field of view it has compared to the whole sky, you can work out that if there are many thousands of galaxies in this field of view, then the total number of galaxies in the observable universe must be hundreds of billions, perhaps trillions of galaxies. So the Hubble Deep Field was a way of us establishing, in a sense, the content of the observable universe. In addition to the scientific legacy, the Hubble has managed to do what many scientific instruments have failed to do. It's managed to bring the public along for the ride. It's touched the public consciousness. When we're thinking about various fantastic objects that Hubble has been able to image, people have said, the laws of physics have created these incredible structures, some of which we're going to see in a moment, and Hubble has revealed them. Through all the research, Hubble has brought the public along for the ride. It's taking the excitement that scientists feel with new discoveries and brought it to non-scientists. So let's just take a few indulgent minutes to have a look at some of these amazing images that the Hubble has produced. This is one of my favourite planetary nebula, the Helix Nebula. It's a little bit difficult to see from the United Kingdom. It's low down in the south during the summer months, much higher in the sky from Botswana. It's a planetary nebula, nothing to do with planets. It's the result of a star coming to the end of its life. So a star like the Sun, when the nuclear fuel runs out, the star will compress, heat up the core, and the outer parts, the outer envelope of the star, could be shed into the interstellar medium. So effectively what we're looking at is the outer part of a star, and what's left of the core of the star is this tiny little thing in the centre, a so-called white dwarf. So in a sense, we're looking at the future of our sun, because our sun, being a middle-sized star, will probably end its life through this particular phase of removing the outer parts of the atmosphere of the star. Once it's expanded through a red giant phase, the outer parts of the star will end up expanding into the interstellar medium and produce a planetary nebula probably similar to this. The antenna galaxies. Here we have a collision of two galaxies. Sounds very dramatic, but you have to bear in mind that the stars are so far apart, it's unlikely that stars themselves will collide with each other. But when two galaxies collide, then certainly the gas within those two galaxies will interact and produce a lot of new star formation. We can see all the pink regions here indicating a lot of new stars being born. So far from galaxy collisions being the end of life of a galaxy, in many respects it's a rebirth of the galaxy as new star formation occurs. The end of an individual star's life, if the star is very massive, could be a supernova. And here the Crab Nebula, which is a favourite object for many amateur astronomers in the constellation of Taurus. Here the field of view again of the Hubble was rather limited, so it had to take a lot of separate images and mosaic them together to get all of the extraordinary structure of the Crab Nebula, a supernova remnant. You must have seen many examples of images like this, various nebula. This particular one is called Mystic Mountain, from the centre of a nebula called Eta Carina, not visible from the northern latitudes, but prominent in southern latitudes. Here, images have been taken at particular wavelengths. The Hubble has imaged at hydrogen and sulfur and oxygen wavelengths and then coloured the images accordingly in what is often called the Hubble Palette, a particular convention for how to colour the images. So in this particular case, for instance, sulfur has been assigned red, hydrogen has been assigned green, and oxygen has been assigned blue, and the combination, the colour image, then not only allows you to see the morphology, the structure of these clouds in the nebula, but also to understand the chemistry. One of my favourite galaxies, the Sombrero Galaxy Messier 104. A rather diffuse but large central bulge and this very prominent dusty band around the girdle of the galaxy. Simply stunning image of a well-known galaxy. This globular cluster, Messier 5, this is a reminder that when clusters are imaged from Earth-based telescopes, quite often it's only the outer stars that can be resolved, because the central part of the globular cluster is so crowded, then individual stars tend to overlap with each other unless you have the sort of resolution that the Hubble is able to deliver, in which case you can resolve individual stars all the way into the core of the globular cluster. And so Hubble is able to, at a glance, capture the image from many hundreds of thousands of stars and essentially resolve them all. Some spiral galaxies can be really beautiful. This one has a very large bar and obviously two prominent spiral arms. It is thought that the Milky Way galaxy has a bar at the centre and 4 spiral arms. There are lots of different structures within the idea of a spiral galaxy. You could argue that no two spiral galaxies are actually the same in terms of the structure of the spiral arms or the structure of the bar which might exist towards the centre of the galaxy. Galaxy collisions are certainly more common than we first appreciated. Here we have what was presumably a spiral galaxy interacting with another, and we can see that the tidal interactions, the gravitational interactions of the two galaxies, is distorting both of them. And it is thought that this is a perfectly natural way that galaxies interact with each other. It's not that unusual, it is essential to galaxy evolution. Galaxies grow by merging and colliding with other galaxies. A large galaxy might gobble up some of the smaller galaxies around it, and large galaxies merging with each other can result in much larger galaxies. And when we look at galaxies at different distances, we hope to be able to get an idea of galaxy evolution by looking back at galaxies that are forming at different points, different times of the universe's evolution. It's one of the reasons why it'd be really useful to look as far as possible, because that of course means we're looking as far back in time as possible due to the finite speed of light, and we would like to see the very earliest galaxies to see how different they are from the sort of galaxies we see around us today. This is another supernova remnant, but this particular one is very large in our sky, called the Veil Nebula. It's many degrees across, much larger than the apparent size of the full moon in our sky. So the Hubble, again, couldn't image all of this supernova remnant, but here it's just imaged one edge of the supernova remnant, which is effectively the shock wave of the supernova as it moves through the interstellar medium. Again, the Hubble here has imaged this particular structure at different wavelengths. Again, hydrogen, sulfur and oxygen, but in this particular case, a slightly different arrangement of the colours. Here, hydrogen has been shown in red, sulfur has been shown in green, and oxygen is shown in blue. But regardless, you can see simply from the beautiful colours that come through in these sorts of images, you can see not only can we get an idea of the morphology and the structure of this shock wave, but we can see the chemical compositions in there as well. And that helps us understand not only the dynamics of supernova, because this is a shock wave moving through the interstellar medium, it gives us more information about what the medium is in between the stars. Similar to pillars of to the Mystic Mountain I showed before, here we have the pillars of creation, seen in a nebula that can be more readily observed from the northern hemisphere compared to Eta Carina in the southern hemisphere. The famous pillars of creation, imaged in the 1990s with the first camera that produced nice sharp images, and this is with the replacement camera, camera number 3, giving us exceptional views of this particular star-forming region. So we're looking at the centre of a nebula which contains hydrogen and oxygen and sulfur and other elements, and these gas clouds are being sculpted by the stars that are irradiating with ultraviolet light and evaporating some of those gas columns. So they are effectively being sculpted by the solar winds of some young hot stars embedded in those gas clouds. And I'll say more about that in just a moment. I've already mentioned the Hubble Deep Field and the importance in terms of understanding the way the universe is constructed, and reminding you that we're looking back in time at the more distant objects, and that is a reason why we would like to move from the capabilities of the Hubble to the capabilities of other space telescopes so that we can see even further back in time. And I'll come back to that in just a moment as well. So what lies beyond? The Hubble has been around for more than 30 years now. Ground-based telescopes have now developed adaptive optics. In other words, yes, the Earth's atmosphere does blur the image from ground-based telescopes, but if you produce an artificial star, as indicated here by shining a laser into the sky and seeing the artificial star produced by the laser, seeing how that is wobbling, you get an idea of how the Earth's atmosphere is affecting starlight. You could use that to compensate for the Earth's turbulent atmosphere. So if you can do that, why bother with space telescopes at all? Now that we have the technology to do that, shouldn't we just abandon the idea of space telescopes? If you look on the right there, the 30-metre telescope, the European Extremely Large Telescope, diameter nominally about 40 metres or so, these of course are absolutely huge compared to existing space telescopes. So if those are coming online in a few years, why bother with anything else? One thing you have to bear in mind is, even with adaptive optics, it's not quite as simple as it sounds. Yes, you can shine a laser into the sky and see how that little bit of Earth's atmosphere is varying. But the Earth's atmosphere is chaotic. Just because you understand how this bit of the atmosphere is varying doesn't mean you know what's going on over here. So you can't get a perfect field of view. You can't compensate for the turbulence of the Earth's atmosphere across the entire field of view that the telescope is able to image. You can certainly home in on a small region. You might be interested in looking at an exoplanet, for instance, and you might be able to get that small region nicely focused and nicely the blurring nicely removed from that particular part of the image, but you can't do it over the whole field of view. If you want to take an image and have it sharp from corner to corner and not affected by the Earth's atmosphere, then adaptive optics is not the answer. You really do need to get away from the atmospheric blurring completely, and that means you need a space telescope. There are, of course, other space telescopes in existence. Kepler has now come to the end of its life, but its mission was to look for Earth-like planets orbiting other stars. It did that with a very large detector. It didn't have a particularly large mirror, but it had a large detector, and it stared at a particular patch of sky and looked at the brightnesses of all the stars it could see to look for characteristic dips in the brightness, which would indicate that an exoplanet has moved in front and transited the star and reduced its brightness. So Kepler wasn't trying to survey the whole sky to see how many exoplanets were out there. It just stared at this patch of sky and found thousands of exoplanets in that region. And that gives us a rough idea of how many exoplanets probably exist throughout the Milky Way. Another mission, this time an ESA mission, has very ambitious aims, and that is to measure the positions of something of order 1 billion stars. So the Gaia mission doesn't take pictures as such. It looks to try and measure as accurately as possible the positions of lots of stars. And if it does that time and time again, then not only can it get a very accurate position for the stars, it can see how they're moving. And that will allow us to get a much better idea of what's going on with stars in the Milky Way. Where are they now? In which direction are they moving? And with what velocity? That helps us get an understanding of the dynamics of the Milky Way. The ESA mission is not in orbit around the Earth. It's at a particular point in space, which I'll come to in just a second. And if we do reflect on the Hubble Space Telescope, if you will excuse the pun of a reflection of the Hubble Space Telescope, we can ask about successors. And I'm sure you know about the James Webb Space Telescope. Strictly speaking, it's not a successor, it's more a complement, because although the James Webb Space Telescope has got something like 30 years technology increase over the Hubble Space Telescope, it was launched on Christmas Day of last year. It too had its own delays in getting finally into its final position. But in this case, the James Webb is a complement rather than a replacement for the Hubble Space Telescope, because it will be working principally in a different part of the spectrum. The James Webb is an infrared telescope, whereas the Hubble is principally an optical telescope. The James Webb mirror is much larger, some 6 or so meters in diameter, compared to the 2.4 meters of the Hubble. So remember what I said very early, bigger mirrors are better because they can give you more detail and they can look at fainter objects. Well, certainly the James Webb will be able to look at fainter objects because it will be able to catch more light. As it happens, the resolution will be very similar to the Hubble, because although the James Webb primary mirror is much larger, it will be operating at infrared wavelengths which are much longer, and the resolution depends on the size of the mirror and the wavelength of light you're detecting. So as it happens, the resolution will be similar. Where will Webb be? It won't be in orbit around the Earth. Like Gaia, it'll be parked at a particular position called Lagrangian 2, or L2. As indicated by this little graphic here, it'll be in orbit around a point in space. It's rather bizarre. How can you orbit around something where there's nothing there? Well, that's due to a quirk of orbital mechanics worked out by Lagrange some time ago. So why would you want to send Webb out there? Why was it okay to have the Hubble Space Telescope in orbit around the Earth, but the James Webb is being sent to a completely different location? Well, that's because the James Webb works in the infrared, and we want to get away from the heat of the Earth and the heat of the Moon. You can see that L2 is on the opposite side of the Earth from the Sun. So if you park yourself at L2, the Earth and the Moon and the Sun are all in the same part of the sky. So if you build yourself a sun shield, you can block out the heat from all of those objects at the same time. So what will the James Webb do? Well, it'll be working in the infrared, and that's why it will be able to see more than the Hubble Space Telescope. Not because it has higher resolution, but because of the infrared. Remember the pillars of creation I showed you a little while ago? There on the left, imaged by Hubble in visible light. We think there are stars inside those gas pillars that are moulding and sculpting the shapes that we can see. But if we were to move into the infrared, infrared is less affected by the scattering that visible light has in these rather gaseous, dusty environments, and then we can start to see what's going on inside, where these stars are forming, these young hot stars that are just being born, and if they are giving birth to exoplanet systems, if they're giving birth to their own solar systems. So by looking in the infrared, we can see more. This particular image was taken by the Hubble because the Hubble is able to work in the visible and can extend its way a little bit into the infrared part of the spectrum. The James Webb will be able to go much further into the infrared part of the spectrum. And the other great benefit as far as the James Webb is concerned is not only young stars, early stars and planetary formation. If the Webb does the equivalent of the Hubble Deep Field, remember the most distant galaxies, light takes a finite time to reach us, so the most distant galaxies are the oldest galaxies in the sense that we are looking back further and further and further in time when we look at these very faint galaxies. Because of the expansion of the universe, the light from these distant galaxies has been stretched from the visible part of the spectrum to the infrared part of the spectrum. So it's expected that a lot of these very distant galaxies will look brighter in the infrared. So the James Webb will see some of these more distant galaxies brighter because they'll be brighter in the infrared, and the James Webb has a larger mirror, so brighter again. So it will be able to see much more detail in these distant galaxies, and hopefully it will be able to see even more distant galaxies. In other words, it will be able to see even more further back in time. The Hubble can probably go back some 13 billion years out of the universe's lifetime of 13.8 billion years. It is hoped that the James Webb will be able to go back perhaps another 500 million years, even closer to that early stage of early star formation and early galaxy formation. So it'll only be a few months, we hope, before the James Webb will be operational. It's been sitting at Lagrangian 2 for a few months, cooling down so that its instruments can work. In a few months' time, we will start to see the results of the James Webb looking at star formation, planet formation, and the very early universe. So I've been telling you about the need for space telescopes and ground-based alternatives. I told you how the Hubble was launched with a faulty mirror and how the optics were fixed. I've given you a taste, and only a taste, of what Hubble has told us about how the universe works and how the public has come along for the ride. And then I reminded everybody that yes, ground-based telescopes are going to be fantastic with their adaptive optics in the future and their huge apertures, but there will always be a need for space telescopes. Thank you for listening.